Production of Autoline this week is underwritten in part by TrueCar and...
Did you know advanced high-strength steels are the leading material used by automakers to achieve the new fuel economy standards? Advanced high-strength steels are lighter in weight and reduce greenhouse gas emissions without compromising safety, performance, or affordability. Steel, a sound, sustainable investment. Today, tomorrow, and beyond. For more information, visit autosteel.org.
You know why I pulled you over, ma'am? I need you to recalibrate the Doppler shift on the return signal. Radar's on the frisk.
Do Sonata drivers know something you don't? The Sonata from Hyundai.
And now, here is your host, John McElroy.
Welcome to Autoline This Week. You know, automakers have got to make their cars a whole lot lighter to make future fuel economy standards. A key way to do that is with carbon fiber. Great material, but we don't know a whole lot about it. That's why I've invited 3 experts to come and talk about where carbon fiber is going in the auto industry. We have Florian Schattenmann, the Global Research and Development Director for Dow Automotive. Graham Henkel is model responsible for the Viper, the great sports car from Chrysler, or I should say SRT. And also Jim Stargard, the president of Plauson, which is a supplier company in the carbon fiber field. And I want to welcome you all to Autoline This Week.
Thank you.
Thanks.
Graham, let's start with you. The old Viper had a little bit of carbon fiber in it. The new one has a whole lot more. Tell us about some of the changes and why you're doing this and what Chrysler might learn from this effort.
Great question. So the new 2013 SRT Viper, as we started the project a few years ago, we had several key objectives, both internal and external. Internally and from a technical standpoint, a key objective for the new car was to reduce weight. And so we looked, of course, at the best technologies available in the world to enable that. And a lot of engineering went on under the skin to achieve that. One of the main contributors to our ability to take over 100 pounds of weight out of the car was a broad application of carbon fiber on the upper body. The new Viper uses a full, kind of a conventional carbon fiber process to produce the full clamshell hood. The roof inner and outer are also carbon, and the rear deck lid is full carbon. So over half of the upper body, if you will, is carbon. And of course, we've used a variety of other materials, cast mag and aluminum and other materials to achieve our end objective. But on the upper body, the carbon alone contributed somewhere on the order of a 70-pound weight reduction to the vehicle, which was significant.
Not only that, you're talking upper body, so you're reducing the center of gravity or lowering it, making the sports car handle even better.
That's right. You'd make a great engineer, John. No, exactly. We had a significant lowering of the CG of the car due to the carbon upper body, as well as some other initiatives we had. So we're really excited. You know, carbon internally for Chrysler, we don't have a huge amount of experience with carbon, but like many automakers, we use our premium sports car as a platform to trial new technologies. And so for us with carbon, this was a great opportunity for us to put a small team of engineers on the carbon application to learn about the processes and the performance and durability and impact tests. And to look forward to the future of what we could do with further carbon applications as the industry enables those going forward. So we're really excited to be about launching the new Viper, but also about some of the projects we have underway for further in the future.
Jim, it's your company, Plauson, that's making these parts for Viper, but I got to believe you're looking beyond that to getting this material out in mass market vehicles, not just a low-volume, expensive sports car. What kind of things does the industry need to have happen to spread carbon fiber to the masses, so to speak?
Okay, there's for the Viper, we're using conventional carbon fiber manufacturing. It's similar to what we've done in the past on the Corvette ZR1, Z06, the Mustang Shelby, and the Viper ACR parts that we had done historically with
So it's very labor-intensive, very slow process, I think.
It is, because of the complexity of the parts, the size, the sheer magnitude of the clamshell hood, and the complexity of a structural roof in carbon fiber drove it to the more conventional technologies. But at the same time, we're doing everything we can at Plauson to drive out the processing costs. Some of the manual processes we're automating. We are at the same time as launching the Viper, we validated and are in the process of commercializing a new process for forming carbon fiber, which basically takes the cycle time down from 90 minutes to 17 minutes. So that's going to allow us to get from 3,000 cars to 30,000, 40, and 50,000 cars. And that's really, and we have that capability here in Wixom, and we're installing that in our new facility in Grand Rapids.
You got to tell me, and don't get too technical on it, but how do you take so much time out of the cycle time of processing this?
If you think about carbon fiber in an autoclave is a giant oven. And what I like to try and describe to people is, if you have a nice thick fillet, which is what carbon fiber really is, do you want to cook it in an oven, or do you want to cook it on an infrared grill? How are you going to get the heat transferred to the resin to allow it to flow and then cure quickly? What we've done is basically backward engineered what happens in the autoclave in a very slow convection process and gone to an induction process that allows us to rapidly heat and rapidly cool the tooling in a very confined environment, much like any other press that you would see, and take that cycle time down from 90 to 17 minutes. Now the enabling factor for us to get faster is there was never a process for curing carbon fiber quickly. So the resin chemistry was adequate. But we now have a process that is limited by the chemistry. So we need companies like Dow and any of the other suppliers in the industry who said they've never been asked for this before, really, to come up with resins that flow faster and cure faster to allow us to take that cycle time down to 7 minutes, 5 minutes, and achieve whatever the entitlement is that we can get from the epoxy chemistry. At the same time, we're going to look also at processes for thermoplastics, because it's not a one-size-fits-all game. For Class A panels, we'll be looking at epoxy resins. For structural applications, thermoplastics offer some interesting dynamic properties and cycle time advantages. So we're looking at how do we integrate the different resin chemistries in with carbon fiber. We have that capability here in Wixom.
Florian, great segue to get in talking with you then. Dow has been a chemical company forever, making all different kinds of plastics and whatnot. Why the focus now at the company? And tell us a little bit of the background of how Dow is really stepping into carbon fiber.
Yeah, we see this as an absolutely huge opportunity at this point. When you look at the automotive industry right now, it reminds me a little bit to what the computer industry was maybe about 40 years ago, where there's all kinds of technologies being tried, being explored, and I think there will be a bunch of different technologies surviving at the same time depending on the application, depending on the region, depending on where the OEM ultimately wants to place the part. So there's lots of things that are happening, but a couple of things seems to be overarching. If you want to go to a high volume, it's got to be automation ready. Everything has to be done by robots. There's no doubt about it. The other part is cycle time. Jim mentioned that already, down to 17 minutes. Honestly, all of our efforts are 5 minutes or lower. Yep. It's really independent of the process. So you have what we call high pressure resin transfer molding. Ultimately what it is, you put the fiber into a mold, close the mold, and shoot hot resin in there. From that moment until you have to take the part out, we can do this in 4 or 5 minutes now, and lower, depending on the application. Other processes, like the pre-preg process, same thing. And a lot of it is about the design of the resin that really holds it all together, and how it sets, how it cures. You got to have very low viscosity for a while, so the resin can shoot in like water, go into all the parts of the mold, and then you have to set it as quickly as possible. And that's really what we call command cure, and that's where we see our differentiator. But maybe as a final part to that, we're kind of fully integrated, right? We have access to the carbon fiber now. We have this Dow-AXA joint venture, the epoxy resin, the adhesives. How to join it, how to integrate it into the vehicle is all different now, right?
You can't weld or stamp or,
but it's not going to last.
Yeah, right. You have to literally glue them together, and you guys have the adhesives to do that.
That's right.
Yep.
And as a last point, none of us alone can do it. So it really requires the OEM, the tier, the material supplier to work together, because you got to kind of explore new grounds here. This is not throwing a new material into an existing process and maybe works a little better. None of us all know exactly where it's going to be, and that's, I think, is the exciting part from my perspective.
2 years ago when I joined Plasan, it was interesting. We were having these discussions with the resin companies, and they were looking at us kind of funny. They were trying to say, well, what do you mean you need something that's going to flow fast with low viscosity and then snap cure? what is your vision? And that's what we've been trying to do, is not only generate the vision, but also putting the infrastructure in place with the processing technologies, whether it be autoclave, whether it be the new pressure press technology for the 17-minute cycle time, or RTM technology, which we have developments going on. You know, we're putting that in place, and we're counting on the material companies to come up with these innovations, these material innovations, so that we can hit the cycle times that we need to satisfy the car companies.
Yeah, one more little add-on, because it also depends where and when the part gets introduced in automotive manufacturing. So if it goes all the way in the frame, it may have to go through the entire E-coat process. So now you have to have this part that's been cured in literally less than 5 minutes. At the same time, it has to withstand temperatures of 200 degrees centigrade or more for a while. So there's a lot of conflicting material properties that we have to overcome, which is obviously job security for us.
And Graham, isn't it a lot of it got to do just with the design of the parts originally? Because I've seen the industry try to take panels made in steel and then try to make them out of carbon fiber and go, this doesn't work too well. Well, they're brilliant in steel, but you have to design differently for carbon fiber, don't you?
No, of course. And so for us on the Viper, that was a part of our objective, was to learn more about the design and performance of the carbon materials. I think, you know, we've taken a big first step with Viper in applying it to our upper body and some of the bolt-on panels. But I think, you know, as Jim and Florian would allude to, the greater challenge for the industry is to identify, you know, the cost-effective structure to allow application of these materials in the core vehicle structure, so you can have something that is much more cost-effective with steel or aluminum on a per vehicle basis. So, I mean, the challenge has been historically with the conventional processes, the high cost of carbon and so on has kind of ruled it out. And so we haven't designed in a lot of those applications yet, but now as you know, there's a number of projects and applications underway to study how do we make floor pans, how do we make rails cost effective.
Any examples? Can you give us for example of what you've learned?
Sure. I mean, there's a number of projects underway currently with U.S. Car and the Composites Consortium, the Automotive Composites Consortium, and so we're, you know, Chrysler is a part of those, of course, and we're participating in a number of those projects. And our engineers are learning a lot about, you know, floor pan structures and other structures and how they perform in a variety of performance tests. But also, I mean, to Florian's point, critically, they have to process through the conventional architecture that we have in place. You know, the industry hasn't been built overnight. It's been there for 100 years, and whether we like it or not, there are body shops and paint shops that follow a certain process in general. And so to get into the volume segment of the automotive marketplace in a big way, carbon's going to need to fit into that infrastructure that exists for the industry.
Florian, Dow must be very bullish on this. So how big do you think this market could grow? What kind of growth are we looking at?
We in Dow Automotive, we see this as growing enormously, 15–20%. It's going to have an induction period because a lot of us, we have to really establish the technology, develop them for the next 3 or 5 years. The growth will not look that impressive, but then it will take off. Mm-hmm. A couple of other pieces have to follow up, right? The carbon fiber is right now a little bit of a bottleneck. Carbon fiber accessibility in general, the
raw material,
world capacity there is not large enough. So far, it served mainly aerospace and sports article and that kind of stuff, and maybe some wind, and that's it, right? And so now automotive is a whole different level, and so they have to keep up going. So like you said in the introduction, the second half of the century the decade will be a big growth for us.
And I think one of the keys is looking at what is the base technology for making carbon fiber, because right now the auto industry is using what's historically been used in aerospace. Yeah. And that's for aerospace properties. Not all those properties we need in automotive.
So we can take the cost of the material down?
Well, we may not need the high level of purity in the base fiber that's turned into the carbon fiber.
Kind of over-engineered.
It's over-engineered right now.
For automotive.
For lack of better terms,
that's right.
Yes. And so what we're working on at Plasan, not only internally with some novel new technologies for potentially making carbon fiber from gas, we're also working as part of the Oak Ridge National Lab consortiums, which we're a founding member, looking at other precursors. From a Dow perspective, can polyethylene be used instead of PAN? Significant cost reduction. They're also looking at lignin, which is basically a plant-based precursor. So we're looking at a number of different ways, because you can only take so much cost out of the process from processing, right, Graham? Yeah. The processor can only do so much. Then there's the raw material. So we have to come up with more effective ways on the cost side, but then also addressing the capacity side. So there's a lot that needs to shake out in the industry. The good news is there's a lot of really great companies working on these things right now. And so the outlook is very promising for a mixture of materials within carbon fiber, not mentioning some of the other materials, aluminum, steel, and those, that we're going to reach the cost targets we need to be at.
Yeah, just one statement around the carbon fiber. The way you make them is you take an organic fiber and carbonize it. And the pan fibers that we just mentioned are very inefficient because you throw most of the molecule out. 70%. So it's going to be high cost, and that's where the polyethylene, what you mentioned here, it's going to be much more efficient in that way. So we'll hope for the best. We need it.
Yeah.
So what I'm learning is the engineers have to learn how to design it. Yeah. The suppliers have to learn how to process it. The raw material suppliers need to come up with new things. What about once it's in the field, Graham? How are these cars going to get repaired? Because you guys are learning this all from scratch. What about everybody in the body shops and the dealerships and everything? This is going to be a big learning curve for them.
Yeah, well, it's not an all-new thing. There is already an existing, although probably fragile, infrastructure in the industry and throughout the world for carbon repair. A lot has been made about, by some European automakers who will fly in the carbon doctor if there's damage to a carbon vehicle done, for example. That is not an optimal repair strategy, of course. But I think they're doing that because in some cases they've used carbon in structurally critical applications, and so naturally, if there is significant damage, you want to be sure that there's a good repair in place before that vehicle goes back on the road. So. But I think through local aerospace repair practices that are already out there for the fleet of planes that are on the ground in the world, and I think carbon repair is not a radical surgery, but it is not as widely known as cutting and welding is historically been for vehicles. So certainly that's an area where we'll have to educate technicians in the dealer bodies and in body shops about the appropriate repair for carbon. And I think the truth is, too, that using the internet is a very powerful service technician training tool, so one that didn't exist in the past. So now we can get information out there and available to service technicians wherever they may be about the right procedures that we expect to be used for repair of, whether it's a low volume or increasingly higher volume vehicles. We can get that information out there and make it available to them just with a couple of, hopefully, internet searches later. So
with the original Dodge Viper, any Dodge dealer could sell the car. Now with it being called the SRT Viper, Chrysler's being very careful which dealerships it allows to sell the car. Is this one of the reasons why? Because they have to have this proper training in working with carbon fiber?
Well, there's a number of things going on. Ralph Gilles, the CEO of our SRT brand, Street and Racing Technology, Ralph is working hard to help us build up this high-performance division. And, of course, Viper is the flagship of our SRT brand. And there's a number of factors behind that decision to limit distribution. But a key one is that buyers who come in looking for high-performance vehicles currently, they're usually very educated about what they're shopping. And often they know more than the dealers they've come into. So we've been very selective about training dealers who are eager to sell Viper and other SRT products, and the SRT brand team has a great training program underway currently to help make sure those dealers know all about the products they're selling and can sell them effectively, and to your point, can service them more effectively once Viper's off the ground here momentarily.
Jim, where do you see the price of carbon fiber going? And, the rule of thumb in the industry used to be...
better be down.
Yeah. Well, what I'm getting at is the rule of thumb, as I always understood it, roughly speaking, was steel was 25 cents a pound, or thereabouts. Aluminum about 75 cents a pound. Carbon fiber, $5 a pound. I don't know where those exact numbers are, but
well, you just hit what the wish list for the auto companies is for carbon fiber, $5 a pound. Today it's
not even there, eh?
No, today it's many times that.
Wow.
But the orders of magnitude are roughly correct. I mean,
yeah.
Kind of somewhere between 10 and 100 times for a finished part. I mean, it's a lot, right?
It's a lot. It's a lot currently. What we've been able to accomplish on the Viper, just through taking carbon fiber from its heritage, which is more of a job shop mentality, no process flow, not a tier 1 flow. By changing that within Plasan, we've been able to reduce the conversion time, conversion cost, even with it still being a very manual process. We've been able to make significant improvements, but you can only go so far with that. The work that we're doing with the new process, the new pressure press process, is driving more cost out of the finished part, but we haven't really hit the raw material. And that's what the activities with Dow, with Oak Ridge National Lab, that I mentioned earlier internally, that we're doing is to take significant cost out of the raw material and out of the process through the chemistry. We tackled process first because for us, keeping the chemistry the same and changing the process meant we could commercialize faster. Sooner or later, you got to pay the bills. So we needed to generate revenue. So we're using the same materials both for Viper and another future program with the new technology. We're using the exact same chemistry because all the bond adhesion work was done, all the paint adhesion work was done. We're there. Now we need to tackle the chemistry side of it. We have a process and multiple processes, including RTM, that are capable of much faster rates. Now we need the materials to come down in cost and come down in cure time so that we can achieve the goals of the car companies of a more cost-effective solution on a higher volume scale.
Yeah, it's really the other way around from steel or so, because the process cost is still dominating the overall cost of the part. In Plasan, us, in the material suppliers, we've done a lot of work, and there's a lot of work to be done to take that cost down as far as possible. The fiber we talked about, that's always a critical issue, and I think with increased capacity and better processing there, that price will come down. And of course, we are working on the resin, but a lot of it is the cycle time, right? Whatever you can do there, it will definitely show up right at the bottom line. And then there is always a little bit of cost for lightweighting. We see that, you know,
nothing comes free.
Yeah, we compete with magnesium in this type of, and those are not cheap metals either. So that's where it's going to play. But all the high volume, fast, short cycle time will really be absolutely critical. So there's no compromise there.
Florian, based on what you're all saying, it would seem to me that structural components are the better application. That is, stuff under the skin. You know, when you get on the skin, it's got to be just perfect. You've got to have, no flaws in it whatsoever. If it's under the skin, well, you don't want a structural flaw, but if it's a blemish, no big deal. Do I have that right? Is structural the more promising application?
I'll start and let my colleagues here to chime in. We actually do see that structural applications are more exciting to us, and there's another point.
And you can
it comes back to
cut weight faster that way.
Exactly. So those are some of the heaviest parts, so you get the best weight savings, but also there's one benefit that we have we're molding stuff. So we can actually have a secondary benefit called part simplification. So something that maybe 15 parts and has to be assembled, yeah, it's cheap steel, fine, but you still have to have a lot of labor putting it all together. We can shoot that part in one shot and we're done with it. So we're trying to be also very opportunistic in how to take cost out on other parts where the fiber is the fiber, so it has some cost. So I think we see a lot of opportunities on the structural side, and I totally agree with you on that one. But
there are two elements to that. One of the things you mentioned earlier to Graham, by taking it out of the skin, you lower the center of gravity of the vehicle. If you take all the weight out under the center of gravity of the vehicle, you're going to raise the center of gravity. So we believe that there's going to be a
lighter weight's always better. I don't care.
Right. But we can help balance that.
Yeah.
Now, structural applications, in primary structures, you're limited by the ability to predict the performance in a crash. As Graham mentioned, in a safety critical item, how is that material going to perform? Carbon fiber performs differently than any other material that car companies have used. The tools are not in place to allow them to predict the performance in a crash event.
But they're evolving radically.
They're evolving.
We're
involved
very
in it.
well.
Yeah.
And we're working as part of a DOE grant that we were awarded along with Oak Ridge and a number of other partners to develop those tools, but they don't exist today. So that's an obstacle that needs to be overcome. But I agree, I think it's going to be a mixture of both. I think there's always going to be a play. There are some performance benefits for carbon fiber in hood applications, for instance, that are very attractive. So I think we're going to see both, and that's why we're focusing on both.
So I think to your point about the cost structure, obviously there's a lot of cost today in the raw carbon material tied to the process itself. Right. And then to Jim's point, there's a lot in the processing cost, both in the labor and the energy cost of the conventional processes. So I think as we take cost out of each of those elements, we'll see carbon very quickly migrate from, where it came into the industry in more decorative applications, right? It was a glamorous, sexy thing to have in terms of trim bezels or exterior. No, it is. Well, of course, right?
People love exposed weave.
And that's where, exactly. And that's where, of course, most automakers have started with carbon integration. But all automakers also recognize that the holy grail of the dramatic weight savings, mass reductions, is going to fall in getting into the structure, because that's where we'll really see the big, more dramatic secondary mass reduction benefits associated with the lighter structure. Now you can provide lighter suspensions, lighter brakes, and lighter everything else that goes along with the vehicle. So I think getting another order of magnitude out by some of the new processes Jim has talked about and Plaisant's developing, and others, will be the key to carbon's future and growth in the next half of this decade.
And I love what you're talking about of, do you leave it exposed and see the weave of the carbon, or do you paint it or whatnot? Of course, up to now, everybody who puts carbon on their car wants to show the world that they've got it. So it's just going to be very interesting to see how that evolves. Some recent concept cars have had a soft paint covering it up, or not covering it up, but not making it look as hard plastic, a little bit softer. But it's going to be so exciting to watch all this develop. And I want to thank all of you for having come on the show today. Florian Schottenmann from Dow Automotive, Graham Henkel, model responsible for the Viper, and Jim Stargard, the president of Plaisant. Thank all of you for having been on Autoline this week, and I want to thank all of you for having joined us.
Production of Autoline This Week is underwritten in part by TrueCar and
Did you know advanced high-strength steels are the leading material used by automakers to achieve the new fuel economy standards? Advanced high-strength steels are lighter in weight and reduce greenhouse gas emissions without compromising safety, performance, or affordability. Steel, a sound, sustainable investment. Today, tomorrow, and beyond. For more information, visit autosteel.org.
Why?
Because plants need water to grow.
Because baseball's played in the summer.
Oxygen and hydrogen.
Because I forgot to get a receipt.
Why?
Why not?
Why?
Why don't you go ask your dad?
Do Sonata drivers know something you don't? The Sonata from Hyundai.